So let me explain. Suppose you have some function of x equals 0, x is n by 1, f is n by 1. So then you can solve this using Newton-Raphson. This is fine. But suppose you have f, x and some parameter alpha. Alpha is a number. So what happens is, this is x. I'm just using one axis. This is n dimensions, of course, but just for graphical purposes. Then it may be that there is some curve like this, right? So as alpha changes, there are different solutions that are found. Now you can take one value of alpha and find an x, then you can take another value of alpha, find another x. In this way you can proceed until you come here and you come here, and then after that you take another value of alpha and you don't find a solution. There is another way to do it, which is to follow this curve. Okay, so that is the basic idea, and the way it is implemented is like this. What we are doing is something called arc length continuation. So we say that, once again, this is just a schematic. So there is x and there is alpha and there is some curve like this. Now what we will say is, we will take one solution and we will take another solution. Let's say we found two solutions. This arc length, we call it delta s. Then we look for another solution which is again delta s away and on the curve that we want. Okay, so the mathematical representation of that is like this. Given, let this point be x1, let this point be x2, this is alpha 1, this is alpha 2, then we will say that the norm of x1 alpha 1, so this is an extended vector, minus x2 alpha 2, this norm is equal to delta s. Then we seek a new x3 alpha 3 such that 1 f of x3 alpha 3 is equal to 0 and 2 x2 alpha 2 minus x3 alpha 3 norm equals delta s. Obviously, this is one solution and this is another solution, but we are going to give it an initial guess that is close to this so that it converges to that point. Then we take one more and one more and one more and one more step, and in this way we trace out the curve. Okay, so let me give you the simplest possible example. Let us say x squared plus y squared equals 1. This is one equation. As you are well aware, this is a circle of radius 1, but what we will do is we will treat this variable x as alpha, and so this is the unknown. So our f of x alpha, which is what we were writing abstractly earlier, in the place of this x I now have this variable y, this variable. In the place of this alpha I have this variable x. Okay, alright, let us see how this works out in MATLAB. So let us go to MATLAB. Over here I have Newton, which I have already sent to you. I have a program written continuation side. You don't worry about this. It has this alpha in here, it has this big X, some variables, it has this continuation program. They are all small programs. You see, this one is just a few lines, this one is just a few lines. Okay, this is the program that you have to write. Okay, so remember, Z, which is x square plus y square minus 1, that is what has to be 0. This is the scalar case. We will do others very soon. And in this equation, which you have derived from some other application, this alpha is a name I have made up, which I am hoping will not be part of your equations. So over here I am saying alpha, and I am saying that alpha is a global variable. Okay, then I come here, let me use this, then I come here and let me say CLC, clear my window, let me say clear all. Then I have to declare alpha as a global variable. Now on my circle I know that for x equal to 0 there is y equal to 1. I know there is such a solution, but what I will do is I will say alpha is equal to 0. I will also say global big X. Okay, so this is the other things you don't have to worry about. This is the one you have to worry about. This is what I want you to remember from the video. Okay, so I come here, I say global big X, also I have to define that variable. I will say y equals Newton junk, and let us say 0.9 is my first initial guess. I actually know that the solution is 1 and it gives me a solution 1. Okay, now I have to arrange it. So the y will be on top and alpha will be below. So I will say big X is equal to y alpha. This is my first point. Remember, I need 2 points for the method to proceed. Okay, so now I say alpha is equal to 0.03, different from 0, nearby point. I am choosing this. Then I will say y is equal to another Newton, and this time you see it is not 1, it is 0.9995. Now I have to put this next to the old one, so I will say big X is equal to big X, which is the old value, and a new matrix which is y alpha. And now I have these two values. Given these two values, I should be able to continue, and then all I have to do is, everything is nothing, I just have to say sorry, that's not what I want at all. This is what I want here, continuation, and then I give it the name of the file, which in this case is junk, would be something else, and I say 10. And when I do this, it runs, and when I look at big X, you see it has gone through. So I had given it 2, that is why there are 2 columns. Okay, and you can see that this X, which is here called alpha, is increased to 0.32. It has to increase a lot more. Let me increase it. Let me take 100 steps now. Okay, so big X now has run many times and it has come to some negative value also, and in this case I can plot it. I want X, which is the second row below, so I can go plot big X 2, that is the X part, big X 1, that is the first row. When I plot it, I should get a circle. Well, I haven't yet fully got a circle. That means I need to take some more steps and then plot it. And when I plot it, you see it looks more like a circle. It doesn't look exactly like a circle because the scale is not correct, but I can do axis equal and look at it again, and you see it's a circle. Okay, so now let me close this. Let me say clear all. Let me say global alpha and big X. Excuse me, but let me now do the harmonic balance equations. Okay, so here is one equation. So I'll have to go back to my junk file over here. Alpha will now I will treat omega as alpha. Okay, so I will say omega is alpha. That is one thing. This z, the two equations, what I will have to do here is I will say a is equal to y1, b is equal to y2. Okay, so those were the equations, or I can call it x here, in which case I will have to write x and x. All right, but I have to define parameters, right? So I have to say parameters. Let's say damping is 0.1. Let us say the nonlinearity a is 0.5. Let us say the forcing amplitude is 1.33. Okay, so these are my parameters, and then I come here and I say z. So this is z, this is the output. So I come here and I say z equals control v, and see I have a, omega square, whatever. This one thing has to be 0, and then I say z is equal to z. Then in the second row I have my other equation. Okay, that's all I need to do. I need to save the file, so I'll save it. Now I come here, I'm going to start. When omega is 0, I know there is a static solution. I have a good understanding of that one. So I'm going to start there. So what I will say is alpha equals 0, right? And then I will say Newton. Let me increase this. Newton. Now junk, but I have to give it some initial condition, initial guess, which I'll just put something 1, 0 and see what I get. Okay, well, it's not far, so it's 1. That's now what I will do is I will say big X is equal to answer alpha. Now you see it is three-dimensional. That is because this is A, this is B, and this alpha is actually omega. Okay, all right. Then I say alpha is equal to 0.03 or 4 or 2, my choice. There's some number. Okay, then I say Newton. I give it the same initial guess. It gives me another answer. This is a slightly different answer. Then I say big X equals the big X that I already have plus answer alpha. Learn the syntax. Now I've got this. Okay, these are the 2 points I need to start my iteration. Then I will do my continuation, and I will take maybe 300 steps. It's done. Okay, so now I have to get my A, B and omega. I will say W for omega is equal to big X 3, so that's omega, and I need an amplitude, so I will say AMP is equal to square root. Let me take the square root of A square plus B square. That's the amplitude. So big X 1 square plus big X 2 square. The square root is closed, and then I do plot omega amp. Well, you can see that it has started and it is still going. It still has a long way to go. So I will say continuation. Let's do 600 more. Okay, then again I have to define omega, I have to define amp, and I have to plot. And come here, and you see this is this is the sort of graph that I had given you earlier. What I can do now is I can say hold on and leave it there. Then I can come here and change the parameters. Okay, so what I can do, for example, is I can make the forcing a bit smaller. So I'll make, instead of 1.33, I'll make the forcing 1. I have to go back and I have to say big X is equal to, just set it equal to blank, alpha is equal to 0 Newton something, and now it is 0.8046, and I say big X is equal to, remember I had done that already, so that is the first value. Then I will say alpha is equal to 0.02, then I will say Newton. I'll run it again and I'll have some other answer. This is the other answer. Then I will say big X is equal to, I'll get there. Now I have two of them. Then I will do continuation and directly go for 1,000 steps, or maybe not 1,000, maybe 900 is what I had done earlier. Okay, then I will say omega equals, and this is my new omega, but I'll call it omega 1, and then I have my amp, not that, and this I will call amp 1. I've already said hold on, so I will plot omega 1 amp 1 in red, and when I go back and look at my figure, you see this is roughly what I was telling you earlier. This one is for amplitude 1, forcing amplitude 1, and this one I can line width 3. Okay, so that's amplitude 1, and this one line width 2, right? So now you can see that is with forcing amplitude 1.33. Okay, for the same thing I can change the damping and so on. So for example, if the damping is 0.4 or something, so it's a higher damping, the zero frequency solution remains valid because damping is not important there, it's just a scalar. So I'm sorry, it's static. So I will go back to my old solution, then I will say alpha equals 0.02, then I will say Newton, there I go, and then I'll say, now again I have two starting points, then I say continuation 900, then I will say omega 1, but then change that to 2, and I will say a amp 1, change that to 2, and then I will say plot and change it to black, and then I'll go here and look. No, that's funny. That's because I didn't save this file, perhaps. The file is saved. Oh, sorry, no problem. I have plotted the wrong one. I have to plot 2. And you see that's what it is. So you see this, because over here, once again let me emphasize, please see my cursor over here, far from the resonant point, the damping does not affect the answer. Over here it affects how far it will rise. From red to blue, force is increasing. From red to thin black, damping is increasing. So this kind of understanding, which I have already described in the previous lecture, we are seeing that it is consistent here. You have now learnt the numerical continuation method. I will send you the files I will send you junk and continuation side and continuation m. Just continuation.m. That's all you need. Thank you. Bye bye.